have him here, and please enjoy the talk.
Okay. Okay, thank you. Hi, everyone, and welcome to today's presentation on large language models. My name is Jiaheng Liu, and the topic of our discussion is large language models. The most popular topic today is over the course of this presentation, we will walk through the foundations and the architecture breakthroughs and the reasoning evolution and the future outlook of these LLMs. Let us begin. First, I will introduce myself. My research centers on large language models, code intelligence, reinforcement learning, intelligent agents, and evaluation systems. I have published more than 100 papers in top international conferences and journals such as SML, NEUROPS, ACLI, and ACL. And I have received the ACL Understanding Paper Award. To give you an outline of today's talk, our presentation is structured into 6 parts. We will begin with part 1, focusing on the foundations and the classical era of LLMs. And in part 2, we will look at the core architecture and training breakthroughs that made the scaling practical. In part 3, we will cover the system 2 and reasoning revolution, which represent a major paradigm that shifts how these models are thinking. In part 4, we will map out the highly competitive global landscape of existing large language models. In part 5, we will discuss the recent agentic technologies. In part 6, we will discuss the challenges, limits, and the future work of large language models. First, in this section, we will revisit the basic probabilities mechanisms of language models, tracing how model size and training data grows, and look at the early development of generative pre-training transformer family. First, our modern narrative of language models really begins on November 30th, 2022, when OpenAI released ChatGPT. This was a milestone that breaks through conversational AI into the mainstream. At that time, Microsoft co-founder Bill Gates said that AI chatbots like ChatGPT will become as important as the PC or the internet. As shows the benchmark chart in artificial analysis at the bottom. This release show a continuous competitive evaluation of models such as Cloud, Gemini, GPT, Grok, or China-related LLMs like Q1, Kimi, or other language models, constantly pushing the limits of the visual and textual reasoning capabilities. Looking at the adoption rate, ChatGPT have reached 100 million monthly active users by January 2026. The fastest growing consumer application in history. And ChatGPT have been applied to a wide range of scenarios, such as question answering, article writing, text summarization, translation, and code generation like Cloud Code Codex. Since the ChatGPT release, the number of LLM-related papers on arXiv have surged a lot. Making the start of the massive research boom. And recent other research has also increased this trend a lot. Before looking at deep networks, let us review the basic definition. A language model is fundamentally a system that compute the probability of a word sequence forming a sentence mathematically. The joint probability of a sentence word is expressed as the product of conditional probabilities, while each word is predicted given the concept of our previous words. For example, if the previous words are where we are, the model aims to predict the probabilities of the next word being going. What makes these models as large? It primarily two things: a massive number of parameters and massive training corpus, as shown on the last graph. The model size grows rapidly from Elmo and Bert and 40 million parameters to GPT-3. And existing models such as Kimi-3 is 30 training tokens. And concurrently, training corpus size expanded dramatically, where BERT was trained on the 3 billion tokens. GPT-3 saw 200 billion tokens, and Chijila in 2022 was trained on 1.4 training tokens, showing that both network depth and data scale are important for downstream performance. To understand how these models are structured, we can classify existing language models into 3 categories. The first is the encoders, like a bot or robot, focusing on bidirectional context and widely used for classification. The second one is the encoder decoders, like T5, BAT, and FLAN T5, which map an input sentence into an output sentence. Last one is the decoder-only transformer families, like GPT, Llama, or Q1, which focus on the autoregressive next token prediction, which is the architecture choice for modern generative language models. Data is important for these language models. Pre-training data is typically split into general test data, such as web pages, conversation tests, and books, and specialized data like multilingual test, scientific papers, and code, where code is an important source for existing language models. This pie chart informs the survey from by Zhao, illustrates how different models utilize different data mixtures. For example, T5 and Falcon relies heavily on web page data, while models like Chijila and Llama mix the web pages, books, and code to build these high-performance language models. Pre-processing these raw data involves several important procedures before it is ready for pre-training. Quality filtering to remove the noise. Deputation uses the sentence level, document level, or set level to reduce the unuseful corpus. And the privacy reduction aim to eliminate personalized artificial information. And the tokenization using methods like byte level BPE or sentence piece. On the right, this table tracks the release time, size, and the pre-training data scale of various landmark models, showing the rapid scale up from T5 1 trillion tokens in 2019 to Llama 2 training tokens in middle of 2023. And existing models may be trained for 30 training tokens. Let's compare the training objectives of autoencoders and autoregressive models. Autoencoders or encoder-only architectures aim to reconstruct the mask response from the original input. The bidirectional context understanding is ideal for this natural language understanding tasks or like classification. On the other hand, autoregressive or decoder-only models predict the next token given all preceding tokens. While they only look forward, they prioritize strong generative abilities, making them ideal for open-ended tasks like summarization, translation, or question answering. Now, let's explore the evolution of the GPT family, tracing its development from GPT-1 up to GPT-4, which established the foundation for existing conversational and multimodal AI. Here is a timeline of GPT family evolution. In June 2018, OpenAI released GPT-1, which explores the pre-training and fine-tuning paradigm. In February 2019, GPT-2 shows that unsupervised pre-training alone can yield strong zero-shot transfer without task-specific fine-tuning. In May 2020, GPT-3 scales parameters to 175 billion, proving that scaling enables in-context learning. By late 2022, InstructGPT introduced RHF, which paved the way for ChatGPT in November 2022. And the multimodal GPT-4 is released in March 2023. Let's first discuss the GPT-1. The GPT-1 builds the pre-training plus fine-tuning paradigm. First, the model just undergoes the pre-training on a large corpus, maximizing the likelihood of net token predictions. Second, it is fine-tuned on supervised downstream tasks using a task-specific classification layer. GPT-1 uses a small model, just 12 layer transformer layers with transfer decoder with 117 million parameters, pre-trained on the book corpus dataset containing about 7,000 unique unpublished books, which is roughly 5 gigabyte of text. This approach proved highly effective in 2018. GPT-1 outperforms the previous state-of-the-art models on 9 out of the 12 NLU tasks evaluated. As shown in this table, it achieved significant gains in natural language inference across multiple datasets, such as LMNLR, SNLR, showing the value of generative pre-training and supervised fine-tuning paradigm for semantic understanding. Then let's discuss the GPT-2. GPT-2 shifted the focus toward unsupervised multitask learning. The author demonstrated that model's capability is the key to the short transfer. The larger the model, the stronger its ability to perform tasks without supervised fine-tuning. GPT-2 was released in 4 sizes, small at 117 million parameters, medium at 345 million, large as and extra large at 1.5 billion parameters, scaling the model dimensionally from to 1,600. To perform multitask unsupervised multitask learning, GB2 free with the conditional probability as predicting the output given by predicting the output given the input and the task type. For example, for translation task, the input is formatted as translate to French, English test, French test. It was trained on the web test dataset containing 45 million links, and which is filtered down to 8 million documents. This is very high quality. The maximum content length was expanded from 512 to 1024 tokens. Without any task-specific fine-tuning, GB2 surpassed the best existing models on several downstream benchmarks, such as Lambda, CPT, and Wikitest2. However, on translation tasks like English to French, its performance remained modest compared to supervised methods, showing that while the short transfer was possible, further skill was needed to make this system practical. Then let's discuss the GB3 in 2020. OpenAI scale up the parameters from 175 billion parameters to this scale. GB3 showed that massive scale unlocks important abilities, which is called in-context learning, where a model can perform a task simply by seeing a few short samples in its prompt, where no training is needed, by passing the traditional pre-training and fine-tuning paradigm. This table shows the family of the GB3. GB3 maintains the same basic architecture as the GB2, but scale up the parameters and expand the training data from 40 GB to a filter datasets of 600 GB. The training mix was heavily weighted toward a filtered version of Common Core, which contributes 16% of this training corpus. And the web test, books, and Wikipedia are also an important training sources for GB3. This slide shows the training loss curves for different versions of GB3. Two important observations can be made. First, given a fixed model size, the gap between the training and validation loss remains very small, which shows that the models are not all fitting to our training corpus. Second, as the model parameters scale up from 100 million to 175 billion, the loss decreases smoothly from the same number of training tokens, which is predictable scaling loss. Here, we can compare different evaluation paradigms. In the traditional pre-training and fine-tuning setting, models are updated on the task-specific loss dataset on specific datasets, which is computational expensive and may risk on overfitting. In contrast, in content learning, which is requires no gradient updates. In the zero-shot setting, the model receives only the task description and instruction prompt. In the few-shot setting, it is given the task description, and we give a few input and output examples, and then we just give the current question prompt, and allowing the model to infer the task structure dynamically and answer the current question. This is an example of few-shot in-context learning on sentimental classification. The model is given a task description. This is a movie review sentiment classifier. And this is followed two examples with the inputs and labeled outputs. First is, I love this movie. The example answer is, this is a positive sentiment. And the second example is the what a waste of time. The answer is negative. This is obviously. And the current input is I joined this movie, and the model is required to answer this question and classify the sentence with positive without any gradient updates. And the training is not needed for in context learning. This chart shows how in-context learning demonstrate in-context learning performance skills with the model size and the number of examples. It is obviously that these are also two clear trends. First, larger models show the significantly stronger in-context learning abilities, and the second, performance improves consistently as we add more in-context examples, showing that few-shot performance is consistently higher than one-shot, which in turn outperforms zero-shot setting. Despite the capabilities of GB3, standard prompting struggle on tasks which require multi-step reasoning, such as math, logic, or code. To address this, the popular chain of thought what is proposed, or COT prompting, by providing the prompting with which requires the model to perform step-by-step reasoning chains. We can elicit the model's reasoning ability. Furthermore, this paper also shows that simply adding the prefix such as let's think step by step in a zero-shot setting, we will get a clear guns on many downstream reading tasks, such as mathematical or logical reading tasks. On the right. However, there is another limitation of raw language models is misalignment. The standard pre-training objective is the next token prediction, which doesn't naturally align with the human values or intent. To address this, researchers established the 3H criteria as AI should be helpful, meaning it assists users in solving their problems. The second is honest, which means it provides accurate answers and express uncertainty. And the third is harmless, meaning it avoids causing physical or situational harm. This is primary for misalignment are instruction tuning and reinforced learning from human feedbacks. Is the RHF, which is popular in today. This diagram outlines the three-step RHF process in JGPT. The step 1 involves collecting demonstrate data to fine-tuning the pre-training models with supervised training, supervised learning, creating the SFT model. In step 2, we just collect several compressed data where a label runs multi-model outputs, which is used to train a reward model. In step 3, the policy is optimized using reinforced learning, such as the PPO algorithm, using the reward model to guide the model output generation. Mathematically, this process involves training the SFT beta baseline, training a reward model using a pairwise cross-entropy loss, which maximizes the score of the preferred outputs over non-preferred ones. And finally, we just optimize the policy using PPO. The PPO objective aims to maximize the reward while adding a KL divergence penalty to prevent the model from drifting too far from the initial SFT policy, as well as optional pre-training gradient term to maintain general performance. Why RHF is necessary when we have SFT? SFT is simple and direct, but collecting high-quality instruction datasets for diverse tasks is expensive. Furthermore, all open-ended tasks, like creative writing, we just have a single correct answer. And the SFT token matching objective doesn't always align with the human preference. RHF address this by using pairwise preference, which are cheaper to collect, although RL training can be unstable and incur commonly problems such as alignment attacks, where performance drops on certain tasks. On March 2023, OpenAI just released GPT-4. This was a major milestone, multimodal model accepting both image and text outputs. GPT-4 achieved significant gains across professional and academic benchmarks, scoring from 90th percentile on the uniform bar example. Although OpenAI doesn't disclose official technical details, industry reports shows that GPT-4 is just use a mutual experts strategy to combine multiple base models for efficient inference. Building on GPT-4, OpenAI has developed a GPT-4V, which integrated the multimodal capabilities. Training was implemented in 2022, and after intensive safety evaluation, it became publicly available in September 2023. GPT-4V follows the same training recipe. Large scale pre-training on text and image data, followed by SFT and RHF, enabling it to interpret visual information and follow interleaved image text instructions. GPT-4V and other related multimodal LLMs supports multimodal input. First, traditional text-only input, and the second is the single image text pairs, and which allow user to upload a diagram or scientific paper. And third, the interleaved image text pairs also enabled, which process sequence of the text and image, and such as the multimodal shopping recipes to calculate totals or identify items across different contexts. In addition, GPT-4V or other multimodal LLMs supports visual pointing and refereeing prompts. It can output coordinates, crop boxes, arrows, circles, and hand-drawn overlays to identify objects in an image or video. As shown in this example, it can locate scientific table columns and identifying objects in a room. Also, geometry problems by reading annotated visual arrows and angles directly from an image. Let's look at the GB4 capabilities, beginning with image description across diverse domains. It can generate detailed descriptions of complex colleagues, identify in the middle. GB4 can identify the landmarks, like the Space Needle in Seattle, analyze the medical CT scans to locate anomalies, and read product logos, and describe dishes like while explaining the cultural origins. GD4 we can also excel on object localizations, counting, and density caption. When presented with an image of several people in the right, in the left, it can output precise bounding box annotations called like box coordinates, and identifies these individuals such as Yanquan, Hinton, Benjo, and Andrew Ng, and generate detailed captions describing each person's background and contribution to AI society. This model can also demonstrate strong multimodal knowledge and common sense reasoning. In the top right, it can solve geometric retrieval, analyze complex food webs to identify producers and consumers. In the right, this one model can also solve visual logic by detecting patterns in geometry rotations and perform detective reasoning to infer the climate tidy habits and building the type of a room. Additionally, it performs well on syntax, table, chart, and document reasoning. Despite these capabilities, GB4V has also notable limitations. It can make errors in detailed physical localization. This is an important problem of existing language models or multimodal language models. This is the hallucination. In the right, such as missing text in complex Chinese characters get confused by rotated charts in the right, such as misinterpreting a horizon bar chart when rotated. These limitations highlights the need for further research in robust visual grounding. Now let's transition to part 2, architecture and training breakthroughs of existing language models. Here we will explore the key innovations that improve the training efficiency and inference performance over the last few years. A major breakthroughs in scaling efficiency is Mistral Experts MOE architecture. In a traditional density transformer, every token activates in every feed-forward network layer. MOE replaces this with a sparse architecture, where a gating network or router assigns each token to a small set of the feed-forward expert layer. This allows the model's total parameters count to scale up while the actual compute required per token remains relatively constant. Though routing quality and load balancing remains an active research challenges. A notable implementation of modern MOE architecture is the DeepSeek V3, which has 671 billion total parameters, but only activates 37 billion parameters per token. It uses extra fine-grained routing with 256 total experts and activating it per token, and incorporates dedicated share expert to capture general knowledge. It also introduced auxiliary loss-free load balancing methods, enabling high performance at a fraction of standing training costs. Another major challenge is the long context inference, is the KV cache bottleneck. During autoregressive generation, the key value cache grows linearly with the sentence length, dominating GPU memory, where grouped query attention and multi-query attention reduce cache size. They can struggle model quality. DeepSeek addressed this by introducing the multi-head latent attention, or MLA, which compresses keys and values into a low-dimensional latent vector, capturing only the latent vector during inference. MLA delivers significant efficiency gains. It reduces the KV cache by 17% compared to standard multi-head attention, and increases the maximum generation throughput reach to 5 times compared to the dense pipeline. This optimization also reduces the training cost compared to DeepSeek dense transformer with stronger performance. Post-training alignment has also evolved a lot. While classical HF where PPO is effective, it requires running on active policy, reference model, reward model, and value metric, value critic, making it unstable and memory intensive. And the DPO was proposed, which derives the closed form maximum likelihood objective directly on preference pairs, reducing the need for a separate reward model for our IL training loop, which also simplifies the post-training pipelines for models such as Llama 3 and Kun. We also have seen a drift from cascaded to naive multimodeling. Every multimodal model is using cascade approach, bridging a frozen wish encoder to the language model using a projection layer, which could lead to information loss and higher latency. And modern naive Omni models such as GPT-4 and Kun Omni train test vision and audio end-to-end. This singular talker architecture enables the model to read all modalities and streaming natural speech in parallel with the test, significantly reducing latency. Finally, the tokenization has advanced significantly. During the GPT-2 era, vocabulary was typically around 40,000 tokens and highly English-centric, which made processing on non-Latin scripts inefficient. Modern models, multi-iterating LLMs using vocabulary about 115,000 to 200,000 tokens with balanced multilingual and code coverage. This reduces the token count for non-English tests and lowering the latency and training costs, which is while supporting dedicated spare tokens such as tools, visions, and audios. Then we will discuss the part 3, which is important and popular topic, is the reasoning abilities of existing language models. Human cognition combines fast, intuitive system 1, which is thinking with slow, and with the system 2 thinking. Standard ARM decoding operates like system 1. It performs on a single forward pass layer for each token without backtracking, which can struggle on this system one thinking process is struggle on complex reasoning or planning tasks. System 2 thinking introduces dedicated reasoning, and where the model explores all native passes, verifies intermediate steps, and self-corrects, spending extra compute at the inference time to solve difficult tasks. As the pre-training phases diminish, the damage returns. Inference time scaling emerges as the key area of progress. Instead of relying solely on larger models, we can allocate more compute per query at the inference time. Strategies include parallel sampling, sequential self-correction, and verifier-guided search methods like MCTS. Research shows that compute optimal test time scaling can also allow smaller models to outperform significantly larger models on mathematical benchmarks and recent many coding generation benchmarks or other reasoning tasks. The system 2, which employs on inference time scaling, also shows significant performance gains. This chart illustrates the landscape of the reasoning models developed throughout the 2024 to 2025. It shows a steady progression of public and private models from early versions like O1 Preview to OpenAI 03 and O4 Mini and DeepSeek R1, QWQ, and the latest releases. This timeline highlights the industry-wide focus on scaling inference time reasoning. This table lists some of notable reasoning models released on early 2025. We've seen a mix of dense and MOE architectures ranging from DeepSeek R1 at 600 billion parameters using GRPO to smaller dense models like Microsoft 5.4 reasoning at 14 billion parameters. Many of these models have adopted GRPO as the primary alignment algorithm. Continuing the previous list, we've seen further models mid to late 2025, including Shanghai AI Labs as Intern S1, Step AI as Step 3, GLM 4.5 thinking, and Baidu's ARM thinking. This shows both the open source and the closed source developers are actively building out reasoning capabilities across multiple modalities. OpenAI O1 models demonstrate the impact on reasoning focus, reinforced learning. As shows the left graph, AIME math accuracy. The AIME is important math benchmarks, which is very difficult. The performance is scaled consistently with the amount of training compute allocated to IO process. In the right graph, we can see the performance also scales with the more test time compute, showing that allowing the model to thinking more and add inference can also increase the performance of existing language models. This slide shows the O1 performance across math, coding, and science benchmarks compared to GPT-4o. On the 2024 AIME math competition, GPT-4o achieved 13.4%, and while O1 have achieved 18.3%. On code forces, which is important coding programming benchmarks, O1 have achieved 1890 percentile, and on the science benchmarks like the GBQA Diamond for PhD level science questions, O1 surpassed the expert human expert performance, scoring 17.88%. This detailed breakdown shows the O1 performance on across more academic exams and categories. It achieves substantial gains on math and physics benchmarks. Like math benchmarks is math Vista, MMLU, and the PhD level science questions such as chemistry, physics, biology. And shows the consistent performance improvements over the classical model GB4O models. And we can see clear improvements on the MMLU categories, include global facts, college chemistry, formal logic, professional law. Following O1, OpenAI has introduced O3 and O4, as shows this slide. O3 and O4 mini achieved further gains on the AME 2024 and 2025 math competitions on code forces. The ELO rating increased from 01 to 2,700, and for O3 and O3 and O4 mini when equipped with terminal access, reflecting significant progress in code generation. On PhD level, science, O3 and O4 mini maintain strong performance. With O3 achieved 18.3% on humanity last exam, HLE, a benchmark of expert level questions across diverse subjects, which is very, very difficult. We can see obviously improvements for O3 models. While the deep research version just reaches to 26.6%. For multimodal tasks, O3, O4 mini also demonstrate strong reading capabilities. On the college level, visual problem solving benchmark MMLU, O3 achieves 82.9 accuracy. It also showed similar performance on math, which this is benchmark, and chart reading, which is outperforms the O1 model. On software engineering and engineering tasks, O3 and O4 mini also shows a solid progression. On supervision verified, O3 achieved nearly 70% on GitHub issues. This also performs well on agentic web browsing, such as browse-com and function call tasks on Taubench, showing that reading-focused training translates well to such agentic benchmarks. OpenAI GPT-5 model integrates the capabilities in a unified system. On the 2025 AME benchmark, GPT-5 Pro with thinking achieves 100% accuracy, while the version without thinking just scores 96.7%. A similar trend is obviously on the science benchmark GBQ Diamond, where the thinking mode improves the performance significantly. For software engineering benchmarks such as Bench Verified and Ada Polyglot, the GB5 will also improve the performance on Bench Verified compared to GB4.0 and Open and O3 benchmarks for showing the performance of GB5. GB5 also achieved higher performance on many multimodal benchmarks, such as MMLU, which is a college-level visual problem solving benchmark, and MMLU Pro, which is a more harder graduate-level visual problem solving benchmarks, and the video understanding benchmarks, video MMLU, which is a video-based multimodal reasoning benchmark, and we can see obvious improvements with the thinking mode compared to the without thinking mode. This chart illustrates the relationship between the accuracy on some bench verified and the average number of the output tokens for GPT-5 and OpenAI O3. Both models show the clear scaling curve, and as we increase the thinking bucket, and we can see obvious performance improvements. And GB5 maintaining higher performance across different thinking buckets on some bench verified software, which is the software engineering coding benchmarks. A major development was the thinking models on open source communities DeepSeek R1, which is released 2025. DeepSeek R1.0 was trained on pure reinforcement learning on top of the base models without any initial supervised fine-tuning, relying on simple rule-based rewards for answer accuracy and formatting, complex reasoning behavior such as self-reflection, verification, and long-chain of thought emerged in the training process. The final DeepSeek R1 model incorporates the cold start data and the multi-stage training to improve the readability and matching the close-sourced models across many benchmarks in the right graph, such as AME, Code Forces, GBQ Diamond, MMLU, Bench Verified. DeepSeek R1 have achieved competitive performance compared to OpenAI O1 Mini on these benchmarks. DeepSeek R1 was made possibly by Group Relative Policy Optimization, or GRPO. Traditional PPO needs a separate value critic model that is, which is often as large as the policy network, which doubles the memory cost requirements for our training. GRPO eliminates the critic model by sampling a group of rollouts for each question, and using the group mean reward as the baseline, calculating advantage based on relative performance. This has become a key training method for existing open source reasoning models. During the IL training process of R1.0, researchers observed a clear phenomenon called the aha moment. The model learned to reevaluate its own intermediate steps, inserting free paraphrase such as wait, this is an aha moment. I can flag here to self-correct. As shown in the graphs, as in the training IL training process, the training steps increased. Both the AME mass accuracy and the average response length has grown significantly from 2000 to 20,000 or more. Which means the model has learned to allocate to more internal thinking time to harder problems. To make these capabilities more accessible, DeepSeek R1, DeepSeek distilled 800,000 reasoning traces from DeepSeek R1 to fine-tuning small open models such as Kun and Llama. Distillation from stronger teachers beats running RL policy directly on these small models, and this result exploration of open reasoning models, QWQ 5.4 reasoning, MIMO, and more reasoning open source models. This brings us to part 4, the competitive global LLM landscape, where we will show the major players and their respective strategies in both the open source and the closed source paradigm. This chart realizes the rapid expansion of LLM landscapes, often referred to the war of 100 models, 100 large language models. Since the release of GB3 in 2020, tech companies and research labs globally have developed their own foundation models, leading to a highly diverse models for both open source and closed source systems. This table summarizes the strategies of key international and China lab organizations. On the international companies, Google has developed the Gemini. Microsoft has is the OpenAI largest investigator, which the OpenAI has developed the ChatGPT, and Meta has developed the Llama models. And Anthropic, which is displayed in this slide, which developed the cloud. The China has developed many language models, such as Alibaba has developed the Kun, and Binance has developed the Seed, and the Hunyuan Foundation model from Tencent, and the GLM, and the Kimi, which is shows the performance compared to similar to which have achieved similar performance compared to these closed source models from compared to Anthropic cloud. At the closed source front, OpenAI and Anthropic remains key competitors. OpenAI includes GB4, and 01, 03, and GB5, and this currently the GPT 4.6 has development, which uses an integrated router to choose between fast and thinking modes. Anthropic has focused on developer-friendly coding with Cloud Code Fable 5, which is also displayed in this slide, and featuring like artifacts and Cloud Code, alongside a strong emphasis on safety research. Meta Llama families has established itself as a key open source standard. The release of the Llama 1 and Llama 2 have accelerated the open source ecosystem. In 2024, Meta has released Llama 3, which scale up the parameter to 405 billion dense parameters, which is trained on 15 training tokens with a context window 128,000 context. Its post-training pipeline utilizes supervised fine-tuning, rejected sample, and integrated DPO per mathematics, avoiding the need for complex PPO training. Alibaba Kun has emerged a highly versatile open-weight family, ranging from lightweight model to larger models. Qwen 3 integrates both syncing and non-syncing modes into a single mode, allowing users to control the syncing bucket. It also utilizes the strong two-week distillation strategy, which transfers ranging capabilities into the lightweight models, making Qwen as one of the most widely used open source families globally. DeepSeek has focused on cost efficiency. The flagship DeepSeek V3 model is, but currently the DeepSeek has updated the version of DeepSeek V4. DeepSeek V3 is a 671 billion parameter MOE models, which is trained for 2,000 more each 800 GPU hours. Its training recipe combines multi-head latent attention, fine-grained MOE, LP8 mixed precision training, and multi-token prediction and MTP. MTP densifies the training signal and enables decoding as inference, having to make high-quality rendering more accessible. Other notable Agile labs include Moonshot AI, which is a Kimi. Recently, the Kimi has released the Kimi K3 models, which is competitive in the globally, and achieves the similar performance with the cloud Opus 4.8. And at the same time, the GRM, which is also a open source model, which is stronger on agents and coding benchmarks. Recently, the GRM have updated the GM for 5.2, which is also displayed in this slide, have achieved competitive performance on the coding benchmarks. Now let's move to the agentic era, beyond the chatbots and to autonomous swarms, where we will examine how we will discuss how LLMs are transitioning from passive conversational partners into proactive agents. This transition represents a significant paradigm shift from passive chatbots. Passive chatbots also respond to single questions based on knowledge frozen at the training time, and with the human user driving each step of this progresses. The proactive agents, in contrast, are given higher level goals. They decompose these goals into plans, actions, and execute actions in live environments, observe the feedback, and integrated this progress by using tools, web browsers, and coding compilation tools. They focus on more complex tasks rather than simply generating tests. This framework shows the 4 core modules of LLM agent. The LLM serves as the central controller or brain. This controller is supported by a profile module that defines the role, and a memory module that manage short-term memory or long-term memory. Long-term based on vector databases, and a planning module that handles goal decomposition and self-reflection, and an action module that executing tasks with APIs, coding, and web browsing. A fundamental framework for agent is React, proposed by Yao from OpenAI. React integrates reasoning traces, which is also called sorts, with concurrent actions, creating a continuous sort action observation loop grounds the model in real feedback. This approach helps ground the model in real-world feedback, reduce hallucination compared to traditional standard chain of thought, and allow the model to recover from the failed actions, such as it also serves a key template for many modern agentic frameworks. To manage long-term memory and prevent hallucination, agents rely on rich RAG. RAG uses external vector databases as a form of long-term memory, retrieving relevant document chunks based on the user queries before generating an answer. This paradigm has evolved from naive RAG to advanced RAG, and the advanced RAG with query rewriting and rewriting and reranking. And finally, many developers have used the modular RAG, which integrates multiple search and routing patterns to keeping agents accurate and up to date without requiring constant retraining. As the task grows more complex, we see a shift toward multi-agent orchestration and agent swarms. Instead of relying on a single agent, multiple specialized agents such as planner, coder, critic collaborate on these tasks. They can organize the they can be organized where a leading agent daily plan tasks to workers and merge the sub-agents results, or through debate and or through debate mechanism to improve reliability. Example is shown in the right. In production include Kimi and Kimi agent swarms, cloud code sub-agents, and collaborative frameworks such as AutoGen and Crew AI. A practical application of agentic swarm agentic paradigm is deep research, implemented in OpenAI deep research and Perplexity labs. These tools automated the multi-step process. First, they decompose a broad question into focused sub-queries. They perform multiple web searches from different sources. Third, they cross-verify and reconcile conflicting evidence across these sources. And finally, they just synthesize the findings into a structured, fully cited research report, replacing hours of manual human search. Another key application is the coding. This is involved from coding completion to end-to-end software engineering pipelines to the like survey agent and cloud code can plan, edit repos, run tests, integrated until bugs are fixed. By 2025, frontier the best agents have shown the ability to resolve over 70% of real-world GitHub issues on Suzhou verified, demonstrate the strong promise of existing coding agent. Let's move to part 6. we will discuss the challenges, limitations, and the future outlook of existing language models. Major challenges is what researchers call the data war. Frontier models already consume a significant room of high-quality public website. As shown in the Epoch AI, the available stock of human-generated public text is projected to effectively exhausted around 2028. To address the problem of data scarcity, researchers has employed the synthetic data strategy, reinforced learning, creating high-quality data, and utilize private and multimodal data sets. However, relying heavily on synthetic data introduce the risk of model collapse, as shown in the loop paradigm diagram. When models are trained on recursively on model-generated data, errors and compound over generations, they can cause the tails of true data distribution to vanish, leading to the loss of risk, rare effects, and mainly mineral styles. Mitigating this requires careful filtering, anchoring synthetic data to high-quality human-level data. Safety and alignment remains a key challenge for existing LLMs. The alignment tags refer to the trade-off between over refusal and can frustrate users, while under refusal can lead to unsafe outputs. Furthermore, models remain the uniform adverse jailbreak and suffix, which can sometimes transfer across different windows. For agentic systems, prompt injection, while agent reads unstructured third-party content and is a notable security risk, requiring robust mitigation strategies such like ID grounding and verifier models. Looking forward, embodied AI is a major future topic, such as vision language action (VLA) models treat robotic control actions as just another set of tokens in the model's vocabulary. Systems like GPT-RT2 demonstrate how website visual language pre-training can transfer directly to robotic manipulation tasks. More recently, the models like Pi0 also use follow matching action experts to control single arm bimanual and mobile robots, bridging the gap between digital tokens and physical movement. Another key direction is the development of world models. A world model predicts how an environment evolves under different actions. Google Genie, for instance, learned to generate playable interactive words from unlabeled internet videos. Modern video generators such as Sora, Will, and the China-related video generation models such as Sedance One are increasingly viewed as implicit physical world simulators, offering a potential path forward toward advanced planning and counterfactual reasoning beyond the standard net-token prediction. To summarize our key takeaways today, first, Skin law establishes the foundations of a classical LLM era. Second, alignment techniques such as SFT, IHF, and DPO have turned role models into useful products or applications. Third, reasoning is a current important topic driven by inference time, compute, and algorithms such as the PPO and many recent distillation methods such as the unpoliced distillation. And fourth, architectural optimizations like MOE and MLE had made this method made these models highly cost efficient. And finally, proactive agents are becoming the primary vehicles to deliver these capabilities to users, such as deep research, coding, and autonomous swarms. And recently, the recursive self-improvement and auto research has become the very popular topic. Okay. Thank you. Any questions?
Thank you for your lecture. Early in your presentation, you discussed advanced tokenization method applied for GPT-2, and you mentioned that it was working only for English. Well, so which languages were used to test these methods, and why it didn't work for them?
Can you repeat this question?
Early in your presentation, you mentioned advanced tokenization method applied for GPT-2 for English, and you said it was working well for English. Which languages else you tested, and why didn't work for them?
The model, the existing LLMs are trained on many data, including English corpus, but the multilingual test data are also trained on this current SOTA models, which can perform well on multilingual scenarios.
Thank you.
Okay, thank you.
Thank you for the presentation. You have tested a lot of models, and from them, which one do you think is the best that you find yourself? And I have seen that Chinese models, they are cheaper to use compared to other models. And why do you think it is that? Like, there are two questions that I want to know about them.
Oh, I don't understand the question.
Okay, I will repeat the question. Which model do you think is the best model that exists right now? Like ChatGPT 5.6 or maybe Llama, Queen, I don't know which one, because you work on this, so which one do you think is the best one?
In current models, currently I just use the Codex ChatGPT 5.6, and the most is the Cloud Code Fable 5. And the open source community, the open source best models is just the Kimi 3, and the recent the Queen 3.8 will be published recently.
Okay, thank you.